Good evening, everyone.
Good evening.
Welcome to People's University Dinosaurs. Evening 4. If you would turn off your cell phones, you know the drill by now. I told you last week about, mouse. We're having a panel discussion on September 20th during Banned Books Week. I called it it's a graphic novel, but it's not a comic book per se. It's far more advanced than that and sophisticated. But it is illustrated. And we'll have a panel of 4 here. If you need a book, let me know, because we still have several copies. And you get to keep the book if you come to the panel. Now this evening, despite our past history, we're going to have a pop quiz. I'm going to deliver this pop quiz at the end of the program. If the first person I call on gets the correct answer, they win a free pizza from Domino's. And we have 2 of those to give away. So there will be 2 questions and 2 pizzas. Isn't that exciting?
Yes. Right. Next week it's 1 coupon.
We will also be giving away in a moment a public market gift certificate. Next Tuesday on the 16th, we will honor the Italian tradition of San Rocco, Feast of St. Rocco, on the 16th of August, and Fair May will be here to play some Italian music and the dancing of the Ohio Valley International Dancers. So that should be a fun show. That's a bunch of books. And then next Thursday, Lindsay is leaving us. So she's going to college or something. So we'll have a new instructor for dinosaur species of Jurassic Park. And his name is Taylor McCoy. He's a vertebrate paleontology volunteer at the Carnegie Museum of Natural History under Dr. Matthew Lamont. I don't see how he could follow Lindsay, do you? He's going to try. I'm sure he'll be great. So like I said, Lindsay's going to Canada to go to school, so we got her a gift. This is a parting gift. It's called So You Want to Move to Canada Stuff you need to know before you go. Stuff like moose burgers and why they hate Americans and everything. So there you go.
I saw a copy of that down at
Okay, before I introduce Lindsay for the last time, I'm going to draw a name for the public market gift certificate out of the little bag. And the name, the winner is Kathy Caldwell. Anyone named Kathy Caldwell? Well, I'll have to get in touch another way. Look it up. But congratulations, Kathy. I'll take my gift certificates. Our instructor is Lindsay Kastroll. She's a paleontology student and museum volunteer with a special interest in dinosaurs. Following her recent graduation from California University of Pennsylvania with degrees in biology and geology, she will be attending a master's program in biological sciences at the University of Alberta starting in fall 2022, where she will complete her research on ornithischian dinosaurs. I thought I was going to get it this time. Triceratops, Stegosaurus, etc. She got her start volunteering with the Carnegie Museum of Natural History, writing Mesozoic Monthly, a series of deep dives on prehistoric creatures for the museum blog. Please welcome Lindsay Kastroll.
Welcome back. Welcome everyone to the 4th class of People's University Dinosaurs. I've given this class today the funky little name of Dinosaur CSI. And so coming to you for the last time before I leave for Canada, I'm Lindsay Kastroll, paleontology student and Carnegie Museum volunteer. And I mentioned last week that my previous lectures were the who, what, where, and when of dinosaur paleontology. And this lecture is pretty much the how we know all that stuff, how we reconstruct the dinosaurs and have an idea of their behavior and their environments. Way more than what you think goes into that, which it's just really cool stuff. But before I begin, I do want to apologize because last week someone asked me about like why the supercontinents broke apart and whether it has to do with like the weight of the continents on one side of the Earth versus the other. And I said, you know, maybe, I don't know. And I was wrong. I looked it up. So what actually happens is with all the continents on one side of the planet, there's so much heat that's getting trapped under those continents that it gets warmer and warmer and starts to melt the crust. So it's not centrifugal force, it's not weight, it is simply heat that is breaking up those supercontinents. It's kind of like a grilled cheese that's melting in the middle. But with that out of the way, we can move on. So pretty much all the information that goes into studying non-avian dinosaurs are fossils. That's a given, right? But what is a fossil? A fossil is basically any evidence of a prehistoric animal, whether that is a footprint, if it's a piece of their body, even evidence that they sneeze, like it's a fossil. So fossils form in a couple different ways, and they differ and look differently based on how they form. First up on here is internal and external molds and casts. How that happens is basically something like a shell presses into sediment, leaves its impression, and then decays away. And then that compressed piece of sediment retains its form and fossilizes that way. We can also see that with an internal mold of that shell if sediment gets inside and leaves, you know, a three-dimensional fossil of what the inside of that shell looks like. And then the outside decays away, and all we've got is that weird little nugget that was inside that shell. So it's really cool for understanding the inside of the internal anatomy of those animals if you get an internal mold. And then there's compression. This is the kind of fossil that we find in like shale pits in this area. So basically a specimen is compacted and compressed down really fine, only leaving like a film of carbon left behind. That gives us a good impression of the outline of, you know, it's usually a leaf. Get a good impression of the outline and like the surface texture, but not so much other bits of that specimen. And it works best when the specimen is laying perpendicular to the angle of compression. So if you have a leaf that falls flat and then dirt piles up on top of it and presses down, that's pretty good. It's going to give you a good result. If that leaf falls a little crooked and then it gets compressed, you're going to have a lot of weird distortion and it's not going to look right. It still happens though, it's just not the same. But I found a couple different fossils of ferns and different leaves like that, just walking around trails around Pittsburgh. So they're really cool fossils, just not what we think about when we think of dinosaurs. Then recrystallization happens when the minerals that make up a specimen, again like a shell, are completely replaced by another material. Minerals are really interesting because even if two minerals have the same chemical formula, that is, the same elements in the same amounts in both minerals, if they're arranged differently in a different crystal lattice, they're going to have different properties, they're going to have different shapes and colors, and they'll be different minerals. And so that's what happens with recrystallization. Water flows in and affects that specimen that's been buried, and the lattice recrystallizes in a different way, forming a different mineral, but just with the same components. And then the big one when it comes to dinosaurs is what is called permineralization. I'm probably going to mess up those syllables at some point tonight. So this happens when a specimen, like a bone, is buried, and groundwater flows through it and seeps into all the nooks and crannies on a cellular level and leaves behind new minerals that fill in those spaces. So it's sort of like an internal mold, but on the cellular level and using minerals instead of just random sediment. Or in the case of some marine organisms, you get pyrite filling in those cells, which is very pretty, but it doesn't usually happen to things like dinosaurs. There's a couple other types of fossilization that I'm not going to cover just because I think these are the ones that you're most likely to hear about. And I really want to get onto more permineralization stuff. So, how does something become permineralized? Step one is easy. You just die. You know, kick the bucket. Uh-oh, we got a pop-up. Good thing I noticed that before it automatically redid it. So you die, you get buried. Those are the first 2 steps of becoming a fossil, pretty much. Piece of cake. And so from there, you just really, the faster you get buried, the better. The longer you go exposed to the elements, the more likely something's going to go wrong. You're going to decay, you're going to be pulled apart by scavengers. Your body is going to preserve the best if you're buried immediately. So you don't want something to come around and nibble on your arm and take it away, and then your body's left without its arm. But unfortunately, most of the fossils we find are very, very incomplete specimens because of this. Or even if all the bones are there, they might not be all in the same place. They might have gotten shifted around because, pieces fell off or tumbled inward or something like that while you were decaying. And this is unfortunately a problem for my beloved Ankylosaurs. They've got all of those pieces of armor preserved in their skin, so when their skin starts to decay, a lot of times they just fall off, and we don't know where they actually are supposed to go on the body. So it comes down to very, very good specimens that were buried very quickly to show us where those osteoderms were during life. Most of the time, you just find a single osteoderm in the middle of nowhere, and the rest of the body is just gone, forgotten, did not get fossilized, but that one piece that fell off did. So it's very sad. But once you're buried, water needs to be able to seep into your cells to fill up your cells with those minerals. Like I said, this usually happens with silica. And silicate minerals can take different forms, just like those other ones I was talking about. The typical silicate minerals that go into a fossil look, something like this. This is our standard T-Rex jaw on top here. Looks a lot like a regular fossil. Sometimes you get things like opal, which is also a form of silica. It looks very different. Usually, dinosaur fossils don't form as opal, but there is at least one example of that happening. This little ornithischian bottom jaw at the bottom here. It's got these leaf-shaped leaves sticking out of it. So once your cells fill with minerals, all you really got to do is just hang out for a couple million years until some chucklehead like me finds you in the middle of the desert. And so it's an easy life once you die, right? So, next slide. So, fossils are preserved in rocks, and they are rocks themselves. But there are several different kinds of rock. So the type of rock really matters if you're going to go out and look for fossils. There are 3 categories of rock. The first is igneous. Igneous rocks are made out of molten rock that has since cooled. This is like when people think about volcanoes, all the lava coming out, cooling. That's an igneous rock. But all of that magma that's coming up at the spreading ridges when new crust is being formed, that's also igneous rock. All kinds of crust are igneous. There's basaltic ocean crust, the granitic continental crust. It's all igneous rock. And this is all very important because igneous rocks are rocks that have a very defined date of when they formed. These are rocks with birthdays, basically. So whenever you want to try and date a igneous rock, you can go in and look at how much the radioactive elements have decayed in that rock. And that'll tell you how long it's been since it's formed. We can't do that with sedimentary rocks, and I'll get to that in a second. So carbon dating, you might have heard of, is something that's commonly used in archaeology. And it's a similar premise. You use the carbon that is decaying in a organic specimen to see how long it's been since it's died. But carbon dating, while it's really great for really recent things, is pretty much done around 50,000 years ago. So for things that are millions of years old, like dinosaurs, we can't use carbon dating. So we have to use other elements like lead and uranium. So while most of the crust is made out of igneous rocks, most of the surface of that crust is covered with sedimentary rocks. These are rocks that are made out of other rocks, basically. So other rocks will get broken down in weather over the years, erosion, all of that stuff, and it forms sediment, little fine particles that eventually get smushed together and get compacted to form these sedimentary rocks. So these, like I said, are not good for dating because every single particle in that rock is very, very old already. So when that rock forms, if you try to date any single one of those grains in that piece of sandstone, they're going to have a date on them from when they first formed in their first rock, not their new rock. So you're never going to get an accurate date with a sedimentary rock. And that kind of stinks because this is the kind of rock that fossils are found in. Fossils need to be buried in sediment, so sedimentary rocks are where they end up. So if we want to date a fossil in a sedimentary rock, we can't directly date it. It kind of stinks. Instead, what they do is they look for an igneous layer below that sedimentary layer and above that sedimentary layer. That gives us the oldest date and the newest date that it could possibly be. We come up with those boundaries. And that's really, really great when those two layers are very close in time to each other. But sometimes there's like a 50 million year gap or something like that between those two layers. So our best guess for that animal is that it lived sometime during this time period, which is not super helpful. We have to keep looking for more igneous rocks around the world that would be around that same horizon to figure out a better date for that specimen. Okay, so sedimentary rocks, they lay down in layers. You get sediment, press it down, sediment, press it down. So usually you expect to see that horizontal if it's going down and down and down. So how come, when I was driving here, I saw rocks in a layer that was going like this, or we see them getting all wibbly wobbly and up and down and around? That comes from metamorphism. Metamorphic rocks are rocks that have been altered by changing temperature and pressure. So we expect that, like most sedimentary rocks, are forming towards the surface, where there's relatively, low temperatures and low pressures. But if that rock gets pushed down farther into the earth, where there's much higher temperature and pressure, things are going to get weird. It's going to get a little soft, and if the continents start compressing like they do in convergence, those layers are going to get squished. They will form ridges and bumps and lumps and all sorts of weird stuff. But if that keeps going farther down into the earth and it ends up melting, that's not metamorphic anymore. It melts and becomes igneous again. So these all link together in what's called the rock cycle. All three kinds of rocks feed into each other. Any rock that gets melted, whether it's sedimentary or metamorphic, will become an igneous rock someday. Anything that starts as igneous or metamorphic is going to erode and become a sedimentary rock someday. Sedimentary and igneous can be changed into metamorphic very easily. So we get all kinds of different interactions with these. And some of them aren't even that straightforward, like in this picture here. So these are the horizontal sedimentary layers of the Grand Canyon. We've got this weird dark stripe that's going up and diagonal, cutting through millions of years of sedimentary layers. This dark streak is what's called an igneous intrusion. This is magma that came up and started cutting through existing layers just because it was hot and going towards the surface, and eventually it cooled and formed an igneous rock in the middle of all the sedimentary stuff. But if we were to go in and look at the rock that is right around the edges of this igneous intrusion, we would find metamorphic rocks, because all that sedimentary stuff has been baked by the heat of that lava or magma as it was coming up through. And also, because metamorphic rocks can start out as sedimentary rocks, and sedimentary rocks house fossils, it stands to reason that we can find fossils in metamorphic rocks, and every so often we do, but they always come out weird and mushed. Like, I can think of a trilobite that has just been sheared in a really weird way. So usually they're not of great biological value at that point. And often we just assume that they're not going to survive metamorphism, so it's not good to look in metamorphic rocks for fossils. Your best bet for finding a fossil is going somewhere with sedimentary rocks. So those sedimentary rocks are the important ones when we're looking at dinosaurs. But sedimentary rocks only form in areas where sediment is being deposited. We can't go somewhere and, like, a mountain is not going to make sedimentary rock, because that is where sediment is being created. At that high, mountain peak, it's being weathered and eroded and making sediment, all those little grains that are coming off those rocks and rolling down the mountainside by gravity and whatnot. But you're not going to get a buildup on there that's going to form new sedimentary rocks. All of that sediment goes down and is going to be washed away by water, wind, glaciers, or just gravity pulling it down. And it's going to end up at some lowlands location where the energy level is too low to keep dragging it onward. So that could be something with, like, a desert, there's a lot of sand. It could be like a meandering river stream where dirt is getting piled up on the bank. It could be, a floodplain where there's just water that rushes out over the plains every once in a while and just lays down a new layer of dirt. So if you want to be fossilized, you want to be somewhere that is one of those low energy environments. If you're going to be on something like a mountain, there's probably tons of dinosaurs that lived in mountain environments, but we don't know what they look like because we don't have fossils from mountains. Sorry, getting lost in my notes again. So rocks get broken down from weathering and carried by erosion. Some sediments form from that erosion, and depending on the size of that sediment, we give it different names. The largest grains that we typically talk about are sand, and then we have silt, and the smallest are clay. And they form different kind of rocks with different kind of, grain sizes. So if you've heard of clay stone or shale, it's made of clay. But that sediment gets carried thousands of miles by currents of water or wind, etc. And then hopefully, eventually, it buries a dinosaur. But all of those grains, once they, finally lay down, they fuse into one big rock with all the compaction of more dirt and stuff on top of it. And that means they're being squished together through the force of gravity, and when groundwater moves through, it's either removing or adding extra minerals that are fusing them all together. So the characteristics of the sediment grains that form the rocks can give us a lot of information about the environment that they were deposited in. For example, the color and mineral type that are found in the rocks could signify whether it was exposed to the air, or if it was underwater, or if that water was high in oxygen, or if it was anoxic. We can also see how fast currents were moving. Because if, like, we have a sandstone, if it's a very sandy rock and there's not a lot of silt or clay, we could assume that the current was slow enough that it dropped all the sand, but fast enough that it was still carrying the silt and clays forward. So the direction those grains take when they settle is also important. If you imagine a bunch of oval-shaped, like, sand grains, you might see them piled up in, like, the microscopic level of a sandstone, piled up like books that have toppled over, so they're all stacked like this. And if we were to look at those, like, getting pushed around by water, the current's going to be facing that way because they all got tumbled that way. So that gives us a great idea of which direction the rivers were flowing in this formation too, which is very, very neat. You might also see what are called sedimentary structures. This could be anything from mud cracks where, like, sediment dried and shriveled up as it dried, or ripple marks in the mud. Even in extreme cases, you get what's called crossbedding. Crossbedding is, like, very fine inclined layers within those horizontal layers that form when, at the edges of sand dunes and very large ripples in the water, at those inclined layers, that's where you get crossbedding. So this is a really good example of cross-bedding on here, because you can see these really fine layers that are going kind of diagonal, and then horizontal layers on top of it. And this is a photo from Mars, by the way. This is one of the reasons why we think Mars had water at some point, because we can see cross-bedding in a lot of its sedimentary rocks. Okay, so there's a couple other kinds of evidence that they can use to reconstruct the environment that aren't just looking at the really lame grains of a rock. That's why I didn't do geology whenever I first started at school, because I was just like, I don't want to look at rocks all day. But it's really cool stuff still. I really do enjoy it. But one of the coolest studies that I've ever read looked at the minerals in dinosaur teeth over several million years, and how the amount of oxygen isotopes changed in those teeth depending on their water source and the humidity in the air, which is just crazy enough as it is. But with that information, they were able to show how far the Western Interior Seaway had moved onto land, because that increased the humidity, and then also how high the Rocky Mountains were starting to get, because that decreased the humidity and brought in more high altitude alpine water sources. It was so cool that they could figure this out just from teeth. But then there's other less complicated ways to figure out things about the environment as well, and that would be like looking at the plant fossils that are in those rocks. A lot of different kind of plants are only found in certain areas with certain climates and weather. So if we can find a certain kind of plant fossilized in these rocks alongside these dinosaurs, we could, assume that it's going to be similar conditions in the weather and climate in that area. Then we can also look at the other animals that are found fossilized in that formation. If you have fish, it's probably a lot of water. If there's crocodiles, it's probably going to be warm. And much more straightforward than drilling into the teeth and figuring out all the minerals and blah, 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 blah. So what's going on around the dinosaur fossils? We've already answered that. We got all the rock stuff. But when we talk about dinosaur fossils, there's a lot of different kinds. We've got the body fossils, which are the ones everyone gets excited about. It's all the bones and feathers and skin impressions and things like that. And then there's also trace fossils, which are extremely interesting because it's every other piece of evidence that they left when they were alive, other than their body that they left when they died. So footprints, nests, their poop, any burrows they dug, those are all trace fossils. I'll start with the body fossils since those are the exciting ones, like I said, but we're going to get the trace fossils, and they're really cool. So, like I said a few slides back, we never find complete specimens, or most often they're not going to be complete specimens. Usually it's only bits. That's what someone who studies taphonomy is concerned with. How do we go from an intact body of a Stegosaurus to this guy, who they call this the Roadkill Stegosaurus, which you can definitely see why. Like, his head is tilted backwards, you can see his chin. All of the little pieces of armor that would have been on his throat have just been scattered around. For whatever reason, his ribs are up here. He's not having a good day. But this is actually a really good specimen. Every specimen of Stegosaurus that they found before this guy was very incomplete and just a huge mess. So much so that when they found it, they didn't know what those plates were for and started reconstructing them like turtle shells over their backs. And that's where it got its name, the roofed lizard. But once they found this guy, this Roadkill Stegosaurus, they were finally able to look at it and go, oh, the plates go on the back, they stand right up like that, which was very, very helpful. So it really shows how taphonomy is a really big deal because it impacts how we're able to study these animals. A body can decay and disarticulate, so it can fall apart or get pulled apart by scavengers. Sometimes it gets transported, like it gets washed into a river or rolls down a hill, or maybe a big aggressive flood comes through and washes them all away. But once it gets buried, You know, hopefully gets buried. But maybe once they're all disarticulated like that, sometimes they're so bad that we can't tell that all those bones are from the same animal. And sometimes we can't tell that they're from the same species of animal. Or sometimes we might have so many that got washed together in a big catastrophic flood that there's a bunch of different species mixed together and we don't know how to make heads or tails of it. So this is really important because it impacts a lot of how we do things. Especially when you think about all the other things that could happen other than disarticulation and travel and whatnot. You have, maybe something big comes by and steps on it and breaks the bones, or, sand grains get blasted against it and it abrades the surface. A lot of things can happen after it dies before it gets fossilized that can really mess us up. But say we get a good majority of the bones in the skeleton, or we use information from very close relatives to fill in those gaps. With those bones, if they aren't articulated the way it was in life, we got to figure out how they were arranged. This is actually pretty, I don't want to say easy, but it's much more straightforward than people like to think it is, because anatomy is very conservative. The basics of how we are put together, whether we are humans or dinosaurs or whatnot, doesn't change very much because there's no selective pressure to alter what works. A lot of our muscles are the same muscles in a cat or a dinosaur or whatnot, just because they work. They attach to the same places on the same bones and do similar things. So using our understandings of modern anatomy and modern relatives like birds and crocodiles, we are pretty easily able to reconstruct skeletons. And I know when I was talking about things like the hips being positioned straight down and the legs being under the body during the first week, I had some people who were kind of skeptical that we could figure that out. But if we were to take human leg bones and human hips and look at the way they connect, there's really only one way that they could connect that would work. If you put them at different angles, you're going to really mess with the muscles, and they might be too short in one way, too long the other way, and it would be very inefficient for movement. So just like us, there's only really one way that those pieces of the femur can fit into that hole on the hip. And that brings me to muscles. So that's also done using our understanding of anatomy that we have from today. Muscles leave scars on bones where they attach. It's a very rough surface, so that tissue can connect. The smooth parts of our bones are much harder to connect to, so that's why we have the muscle scars left over. And so we assume if something has a very large muscle scar or a very large attachment point, it's going to have a large muscle attached to it. And it might be something very important that's holding on to, shoulders that are turning the entire body when you want to swing your tail, or, holding the tail up. Very complicated, heavy parts of the body we assume have these big, heavy muscles. But to figure out how the animal moved, on top of all that, sometimes we can do biomechanical studies, where paleontologists recreate these bones in a 3D computerized environment, and they'll basically test it like they test bridges and buildings. They'll do stress tests to see how far the body can move without stressing the bones, pretty much, or stressing those joints, which is really neat. So it's not just the meat and the movement that we're trying to figure out based on these body fossils, but also the menu. We can generally figure out what dinosaurs ate based on their teeth. Like if you find sharp teeth, usually that's a carnivore. And there's different kinds of sharp teeth, like different amounts of serration and just conical shapes that will influence, different hunting strategies. But we can also use different things than just teeth. Sometimes we'll find specimens of meat or plant-eating dinosaurs with a bunch of rocks in their abdominal cavities. And if we can eliminate the fact that maybe these are just rocks that tumble in there after the animal died, which is pretty easy to do just looking at them, usually these are called gastroliths. A gastrolith is a rock, usually numerous rocks, that a dinosaur will eat, or lots of animals actually. An animal will eat and it'll hang out in their stomach, and grind against other rocks to help break up stubborn materials, like really tough plants. So if we find a plant eater that has gastroliths in its abdominal cavity, it's probably one that eats really, really tough plants and doesn't chew its food. So it really needs a different way to break all that up and get the nutrients out of there. Other times, we'll get lucky enough and actually find remnants of the animal's last meal in its abdominal cavity. Usually this takes the form of there's a fish skeleton that is inside the abdominal cavity of this dinosaur. But sometimes we get really cool stuff. So these two photos on top here are of the same animal. This is the painter's recreation on the left. This is an animal called Scipionix. It's a theropod dinosaur that was only a foot long, so it was really small and cute. And if you look at the belly of this fossil, it's got this really gross brown tube that comes around and loops and goes back through the back legs and stops near its butt. That's its actual intestines. This animal fossilized a lot of soft tissue just like it did its bones. In the process of permineralization, any kind of tissue, as long as it's been buried well enough, can be replaced by those silica minerals. So this is a hard piece of rock, even though it looks like a gross, fresh piece of poop. And so in this preserved organ here, we can see things like its last meal. There is a lizard and a few different fish preserved in Scipionix's intestines, which is just amazing, the level of detail that can be seen in this one specimen. But even if soft tissue doesn't preserve, sometimes we can reconstruct some of those internal organs. This can be done using a CT scanner and scanning a dinosaur skull to map out its brain case. We assume that the brain is going to pretty much exactly match the shape of its brain case. We call this a brain endocast. And since anatomy is conservative, we can say all of those regions on the brain that we know correspond to different senses and abilities are probably going to match on those prehistoric animals as well. So once we get a brain endocast, which usually looks something like this, which doesn't look like much to me, or many of you I'm sure, we can look at it and say, okay, the region that corresponds to smell is just huge on this animal. So it probably used its sense of smell a lot. It was a very refined scent. Or sense. But we can also do other things with it. So this animal that is on the slide, this is the skull of a sauropod called Sarmientosaurus. We've got a digital reconstruction on the left. The actual skull is over here on the right. Dr. Lamanna, who's doing that tour in the 8th class, this is him right here. He helped work on this animal, and they've got this reconstruction at the Carnegie Museum, which is really cool. So what they did is they put this skull in a CT scanner, they got the brain endocast, and they looked at it, and the ear region of this brain was really weird. It was kind of twisted compared to what you usually see in sauropods and other animals. And since the ear is really important for balance, they said that this weird twisting actually means that the head was held at a different position than we usually think of. So Sarmientosaurus probably ate very low-lying vegetation compared to other sauropods because it held its head downward and was able to eat like that, as opposed to other sauropods, which are usually up like this, eating high vegetation. So we can see different feeding strategies just based on brain scans, which is really cool. So the tissues of bones themselves can also be analyzed for more information. Analyzing the cells in bone is called histology, and since I knew I was going to mess it up, permineralization fills those cells, we can get a pretty good view of them if you cut open a bone and put it under a microscope. Unfortunately, this is not done very often because once you cut open a bone, you can't put it back together. It's a destructive method, so it's kind of sad when it happens, but you get so much cool information. It's really great because the long bones of the body, things like the femur, will actually preserve what are basically like tree rings. We call these lines of arrested growth, or lags. Those are lines that show when you go from a time of rapid growth to a time of very slow growth. We assume that those are times like seasonal differences, like summer versus winter when there's not a lot of food. And so these are assumed to be annual rings. So if you cut open a femur and take a look at all those lines, you know, I've got them mapped on here with these little arrows, you can pretty much count the age of that dinosaur just based on those bones. And then once you are able to age a couple different animals from the same species that are different sizes, you're able to figure out how fast those animals grow, which is the growth rate. And that's actually how they were, or one of the reasons why they figured out that dinosaurs are warm-blooded, because cold-blooded animals don't grow as fast as we can see that dinosaurs did. So what I think is the coolest thing about this, though, is that histology is the only way we have to sex a dinosaur. Female dinosaurs, including birds, whenever they start producing eggs, they will reabsorb calcium from their bones to start putting it towards eggshells. So that leaves a different kind of bone in its place called medullary bone. So if you cut open a dinosaur's leg, take a look and you see medullary bone, you know that's a lady dinosaur because it was producing eggs. So body fossils can show us different pathologies as well. So different things that the animals suffered from. You might see injuries like bite marks or holes in the bones like what's seen here. This is a very unfortunate Allosaurus that got a hole punctured in its vertebrae by a Stegosaurus tail spike. We've got the dramatic reenaction right here. They put a spike just right through it. But you also get different illnesses as well. Things like infections, cancer, arthritis, gout, bone spurs. Dinosaurs had tough lives, and we can see evidence of those on the bones. We get like weird growths and stuff. It's really cool. I keep saying that, but it really is really cool. You know, when we're lucky enough to get that sweet, sweet soft tissue preservation, we can sometimes see evidence of color. When it comes to feathers, there's two different kinds of color that we can kind of analyze them for. There are pigments, and then there's structural color. Structural colors are produced by the way light refracts around the structure of the feather. So it's not an actual pigment that you could see with your naked eye. It's just light bouncing around in a cool way that we pick up on as color. So both of these animals here, Microraptor on the left and Kaihan on the right, are iridescent. We're able to look at their feathers, which are preserved well enough that they have iridescence. Like we can see the structures that produce iridescence on their fossilized feathers. So we know pretty much what they look like. But then with pigments, we get even cooler stuff. So pigments, when it comes to pigments, the fossilized versions we see are called melanin. We have melanin. Dinosaurs also have melanin. Melanin is carried by cells called melanosomes. And there's two different kinds of melanosome. There's one that is orangey brown and one that is black. So on something like, I think this is Ankylosaurus. Yeah, Ankylosaurus in the middle here with its red crest and like gray and black pattern on its body. We know pretty much the pattern because they were able to go in and look at the different kind of melanosomes that were preserved on its feathers, which is just incredible. And then this dude is super cool. I called this the red panda dinosaur in a previous lecture, I think. So this is the fossil of Sinosauropteryx on the right here. And you can see it's got these dark feathers around the eyes. It's got these stripes on its tail. So all of these feathers, we know exactly what this pattern looked like. It looked pretty much exactly like this on the left. And that's so cool. It is so cute. But the next one is my favorite. It's one of the most incredible fossils ever found. This is Borealopelta. Borealopelta is an ankylosaur that's preserved on its back on a riverbed. So all of the sediment filled in all the little nooks and crannies and preserved the osteoderms exactly where they were during life. And it preserved pretty much the entire back and face of this animal, so it looks like it's just sleeping. And so it's not just an ankylosaur, we know that it's a nodosaurid, which are the ones that don't have tail clubs but have these big shoulder spikes. And we can see that sticking off the side up here. And so I just think it's so cool that we have basically a mummy of, like, it looks like a dragon. It's pretty neat. And we have all the osteoderms in the right place instead of them just falling off and rolling around in the water and getting lost forever. But most importantly, all of this amazing preservation also preserved skin impressions. And with those skin impressions, we were able to look at the melanosomes of Borealopelta. And what we found was that the back of the animal was like a rusty orange color, and then the belly was like a light cream, and these giant spikes on its shoulders were white, bright white. So this is pretty much what Borealopelta looked like. It's a handsome boy, right? Now, the color of animals doesn't exist in a vacuum. It's fun to imagine dinosaurs as like bright pink or bright green, but we know that color usually has a purpose in animals, so dinosaurs were probably the same way. And there's a couple different ways that we can think about color in these animals. A pattern where it's dark on top and light on the bottom is a camouflage pattern called countershading. It is a natural way of counteracting against the way we usually see shadows form, which shadows are on the belly, not on the top. So it kind of hides the shape of the animal as it moves around. And of course there's other kinds of camouflage as well, like spots and stripes, that help break up the animal silhouette. So we assume that dinosaurs probably would have made use of these strategies just like modern animals, to hide from predators or maybe hide from prey. But similar but different, we have warning coloration as well, where very, very poisonous or venomous animals will have bright colors that say, don't eat me because then you'll die and neither of us will have a good day. Just leave me alone, we'll be fine. And it's a very effective use of bright colors. So effective that harmless species will mimic those dangerous ones and piggyback off of the success of that strategy, so nothing will eat them. But looking at Borealopelta, we see the counter shading, but that doesn't account for these bright white spikes. These kind of break up the silhouette, or in a bad way, not a good way. So there's other things at play here, other than just trying to hide from predators. So there's two different ways that we can think about these bright white spikes. We could call it sexual display, or we could call it species recognition. Sexual display is basically just, what we think of in birds. The bright colors attract a mate. And we assume that a lot of dinosaurs probably had this too, especially when they have display structures. Maybe a giant spike would be really nice to the ladies, or, Triceratops' frill could have been a bright color because it's got a big surface to display on, or Stegosaurus' plates on its back. But these could also be features of species recognition, just ways to show hey, I'm part of the same species as you, we're cool, right? So there's a couple different ways. We like to favor the sexual selection thing just because it's a little more fun, I think. But species recognition is a very valid hypothesis as well. So that's all I have on body fossils. So time to move on to trace fossils, and I promise they're just as exciting. So where body fossils are evidence of an animal after it's died, the trace fossils are literal evidence of what this animal was doing when it was alive. Trace fossils are studied by what are called ichnologists, and they are given names just like other fossils, but we call them ichnospecies names. They're not the same. So a T-Rex fossil footprint and the fossil footprints, and the T-Rex that made that footprint could have different names, but they're the same thing, really, if that makes sense. Just because we study them differently, we need different names. One famous example of a trace fossil is what we call the devil's corkscrew. It's this thing on the left here. When these giant corkscrew structures start eroding out of the hillsides in 1800s Nebraska, people got kind of freaked out by them, hence the name Devil's Corkscrew. But after a while of studying them, they realized that they are trace fossils, and they are burrows of little ancient beavers that lived after the dinosaurs. So we started finding these little beavers down in these little cubbies that are off the side of these basically spiral staircases that they would dig down. And so sediments would fill into those burrows and preserve them as actual structures, and that's why they're trace fossils. And then the actual little beavers inside are still body fossils. So unfortunately, identifying the maker of a trace fossil is extremely difficult. Sometimes it's as easy as the Devil's Corkscrew, where the actual maker is inside of it, or in the case of this ancient horseshoe crab, it literally left its own footprints behind it as a death march. But it's not as easy as that usually. So scientists really just have to go about process of elimination, trying to figure out who left some of these trace fossils. 99% of the time, it's best guesses or most educated guess. Halfway through my notes, they started printing front and back, so I'm getting real confused now. So, footprint fossils are like the quintessential trace fossils, right? Everyone gets really excited about dinosaur footprints. Most of the time, like I said, we aren't sure what made those prints, and that's why they get their own names, so we can make sure we keep track of which ones we're talking about. Those most educated guesses, though, can get us pretty close. For example, this picture here is a giant three-toed footprint that we're pretty sure came from a T-Rex, because T-Rex is a giant three-toed animal that lived in the same time, same place, and there's no evidence of a rival existing in that same area at the same time. So that's probably from a T-Rex. And then the picture on the right here, and they even outlined it to try and make it more visible. I don't know if it's really visible on the screen as much, but it's a very long four-toed foot. That one they called Macropodosaurus, and that's the ichno name. But they figured out what the fossils that made it are, and they think it's Therizinosaurs. Those are those really tall, goose-like theropods that ate plants and had giant claws in their hands. But the most exciting part here is the picture in the background. Just like 2 years ago, people exploring a cave in France found sauropod footprints on the ceiling, where sauropods walked around, they made depressions in the earth, and all the rock underneath those depressions eroded away, leaving these divots in the ceiling of these footprints. So there's these tiny little people in the distance in this photo, and then there's 3 different trackways on the ceiling. In these caves, I think I remember, to get to this cave, it's like 100 meters of crawl space that sometimes flood. So terrifying to actually get there. So I don't know how often we're actually going to see these things, but they're neat. So they gave these sauropod footprints the name Oxytanopodus. And they're similar in size and gauge, like the width of the hands away from each other, to macronarian sauropods. Those are the ones that had really long arms compared to other sauropods. And these footprints don't preserve really big thumb claws like we would expect to see on some of the earlier members, or like a Diplodocus or something like that. So that limits it down to either a Brachiosaurid or a Titanosaurid. So it's not an ideal, like, down to the species level identification, but it is process of elimination on the way, pretty good. But once we have an idea of where those prints came from, they can tell us a ton about the way those dinosaurs walked. For example, we have hadrosaurs, the duck-billed dinosaurs, so something like this guy in the bottom left. They are what we call facultative bipeds. They can walk on 2 legs or 4 legs as necessary. We have trackways showing both ways of walking. If it's a quadrupedal walkway, we can see the large, three-toed, broad footprints from the back feet, and these little, like, stilt-like dots from the front feet, kind of like, you know, they're standing on its toes like a horse. And you can see that kind of in this picture in the bottom left. But then, we can also see whether these dinosaurs were digitigrade or plantigrade. Most theropod dinosaurs are digitigrade. That is that they walk on their toes. Raise your hands if you've ever heard someone say that dinosaurs or birds have backwards knees. I got a couple nods in here. Some people will say that dinosaurs have backwards knees because they look at the ankles, which point the opposite direction. So they do have funky looking legs, but their knees are regular forward pointing knees, and their ankles are where things get funky. So with this Therizinosaurus on the left here, it's walking on its toes, and its heel is going to be somewhere up here by its ankle. So modern cats are digitigrade. They walk on their toes, and their ankles are up off the ground. We assume that most theropods are like this, but when we found those Macropodosaurus fossils, the ones that were hard to see, they were the long four-toed ones on the previous slide, things started to change. So in contrast to digitigrade, we are plantigrade. We walk with our heels planted on the ground. And for the longest time, we thought none of the theropods walked like that, but with those Macropodosaurus fossils, they pretty much exactly match what a Therizinosaur foot would look like if it was walking down on its heels. So we probably wouldn't have known this just looking at the fossil, just based on the way we think about other dinosaurs, but these Therizinosaurs are probably walking flat-footed just like us. And similarly, other piece of paper now. Similarly, footprints give us confirmation that the raptor dinosaurs, the dromaeosaurs, walk with their big toe claws held up off the ground. Because we find footprints of them where we got the two regular toes, and then there's a little stub where that extra, like the other toe with the big claw, was lifted up. So it's just a little stub that's touching the ground. So we have confirmation of that, which is neat. And then when looking at prints, we can also see how far the hands and feet rotate inward or outward as they're walking, or how far apart the hands are from each other compared to the feet. And all of that implies how we reconstruct the limbs. So it's a lot of important information we can gain from that. But lastly, some of the other information we can get out of these trackway fossils are things like we get from Bellatoripes, a kind of tyrannosaur footprint. Bellatoripes preserves a trackway of three tyrannosaurs walking together. So they were traveling in a group, not just a single T-Rex living on its own, as we usually think about it. So these could have been pack-hunting, family group tyrannosaurs. And plus, looking at how long a tyrannosaur's leg is compared to the stride length we see in those footprints, we can estimate how fast they were going. The ones in Bellatoripes were going like a leisurely 4 to 5 miles per hour. 425, not 45. So just strolling along. The walking traces aren't all we have. Sometimes we get swimming traces where you see like 3 claws just like struck the ground and clawed a little bit as it's swimming along. Or you get a sitting trace, like this guy on the right. And the trace fossil that inspired this one on the right is really neat because we can see those heels coming down to rest on the ground. We can see the hands even resting on the ground too. He's resting his knuckles and just hanging out. But going back to the question of what's on the menu, we have coprolites. These are fossilized dung. It's very hard without seeing with our own 2 eyes what a dinosaur poop looks like as it comes out to match a fossilized piece of poop to the dinosaur. Sometimes it is easier though, like with sharks. Sharks have an organ inside their intestines called a spiral valve that slows down food as it goes through so they can get more nutrients out of it. So a shark's poop comes out spiral shaped. So it's pretty easy to tell what a shark poop looks like when you find it in the fossil record. Dinosaurs don't have a spiral valve, so we get lumpy things like this. And at that point, we can only look at what is in it, like what kind of food that animal ate, and make our best guesses at what ate all that stuff. So there could be bones in there with teeth marks, and you can try and figure out what kind of tooth bit that bone before it got swallowed. You might find plant material, and you have to figure out, okay, if this is a really tough kind of plant, maybe it's one that had gastroliths in its stomach. Or if it ate crustacean shells, did it have a wide enough mouth to eat a crab? Things like that. And sometimes we can get trace fossils on these trace fossils, where like a dung beetle or something will go and tunnel through this dung, and you get a trace fossil of that beetle passing through on the trace fossil of the coprolite. And we also, funnily enough, can have urolites, which are impressions where dinosaur pee hit the ground. I don't know a lot about that or how they figure out what a urolite looks like, so I didn't put that in here, but I think it is pretty cool that they can do that. But just like the devil's corkscrew, we can also get dinosaur burrows. So they're not quite as scary with the name. And as far as we know, or as I know at least, we've only found one dinosaur burrow so far, and it was one that contained an adult and two little babies of this species called Oviraptorod, which is a small early ornithischian. So it walked on two legs and looked sort of like a duck-billed dinosaur, or maybe an early ceratopsian. It's weird and in that gray area. But we found an adult and two babies in that burrow. They were all living together, so they probably had a family structure, and that burrow got filled in with sediment, and they died and got preserved like that. So we can assume that other ornithischians of that same size and shape might have also been burrowers as well. And with that family structure, it finally brings us to eggs. Eggs are really, really cool because they can tell us a lot about a dinosaur's reproductive habits. They can come in tons of different sizes and shapes, ranging from spherical to elongated. Maybe they're symmetrical at both ends, or maybe pointy just at one end, like a modern egg. But no matter what, their shells are usually made out of a hard calcium carbonate material, just like modern eggshells. Sometimes though, with the very early dinosaurs, if we find an embryo, we just find a little film, like a halo, around that embryo. They think those might have been soft shell eggs. So dinosaurs might have started out with soft shell eggs, and then somewhere along the way evolved a hard shell and kept that around until modern birds evolved. But no matter what, those eggs have a very rough texture to them that is not seen in modern bird eggs. Those are usually smooth. There's a lot of ideas of why they might have that rough surface. Sometimes they think maybe it's for better gas exchange, but there's not like one idea that they've settled on, like, yes, this is it, you know? But sometimes, just like skin impressions, we can also see pigments in we can also see pigments found in these fossilized shells. Some like bird relatives, some of the closest relatives to birds, like those raptors and the Oviraptorids, we've seen red-brown and blue-green pigments in their eggs. So at some point, those pigments showed up and stuck around until birds evolved, because we see things like robin eggs that are also blue and speckled and cool like that. Oh, and in modern bird eggs, bright colors correlate with the males taking care of the eggs, which gives us more questions to ask about those colored dinosaur eggs, because that might mean male dinosaurs were taking care of those eggs, which is a very cool concept as well. So I talked a little bit about Oviraptorod nests in week 2, but just to recap, we found several fossilized nests in this configuration where there are a circle of pairs of elongated eggs, like 2 by 2 around a circle, with a big divot in the middle where the adult would sit and brood over those eggs. And oxygen isotope studies on those eggshells show that those eggs were incubated at a temperature of like 86 to 100 degrees Fahrenheit, which is pretty neat. They're showing that they're being kept warm by an adult. And the fact that these eggs are laid in pairs is significant because it means that they had 2 oviducts. They were producing 2 eggs at once. Modern birds only produce 1 egg at once. They've lost one of their oviducts. So these dinosaurs hadn't evolved that feature yet. So sauropods also made nests, but they were much less elegant. Their eggs were large and spherical, kind of like soccer balls, instead of those long, elongate ones. And that soccer ball shape, in my mind, probably helped brace it for the impact from that far drop. But I don't know. That's just me guessing. But what they did was they used one of their giant back feet, like this down in the corner here, to scoop out a very long, tapering ditch, basically. And then they lay their eggs in the ditch. And these eggshells, they've seen, have a high vapor conductance when they look at them microscopically. And modern eggs with high vapor conductances are usually covered with dirt or plants to help incubate them. So it's possible that titanosaurids covered up their nests with dirt or plants to help keep their eggs warm. So the most famous dinosaur when it comes to nests is Myosaurus. This is an animal, it is a hadrosaur, one of those duck-billed dinosaurs, and they found it with tons of nests filled with eggs and even baby dinosaurs that weren't able to fend for themselves. So they were able to tell that these dinosaurs were doing parenting behaviors, and that's where its name comes from. It means good mother lizard. Myosaurus laid spherical eggs in a large mound in the center of a large mound. So they weren't sitting on their eggs, they were containing them in that divot in the middle. And since they weren't able to sit on their eggs, they probably covered them up with plant material just to keep them warm. But the interesting thing is, when they found this large spread of Myosaurus nests, all of these nests were spaced about 7 meters apart. And an adult Myosaurus is 9 meters long. So these guys were really packed in together. So they were probably very social animals if they're this cool with hanging out around each other, which gives us a lot of interesting information about, the dinosaur social life. But with all that information from body fossils and trace fossils, I wanted to take time to put it all together and show you how we use all that information to recreate a dinosaur's habitat. We can do that best in, I'm going to mess this up, I didn't take German class, so Conservat Lagerstätte. It's probably not pronounced like that, but these are close enough, yeah. These are locations where the fossil preservation is so good that we have many, many specimens with very good, soft tissue and colors and things preserved. Lagerstätte are very important locations because that's where we get things like Archaeopteryx, the famous bird ancestor with all those feathers. I decided to use the Las Ollas Lagerstätte from Spain for this example. So the rocks of Las Ollas are laminated limestone rocks. You can see them in the back of this picture here. That is a euro coin for scale. So we've got all of these really fine layers of sedimentary rocks that were laid down in a freshwater environment with pretty gentle currents that aren't making them cross-bedded or anything like that, resulting in these very thin layers. And within those rocks, there are 3 different kinds of plant communities. There is a deep lake or pond community with green algae. There is a swamp or marsh group with conifers. And then there's a dry savanna area with tree ferns, which shows that no matter how wet this area was, the climate was pretty arid and dry because of that savanna area. But the real star of Las Ollas are these microbial mats. Microbial mats are things that we still see today where we get really thick layers of microorganisms like bacteria, or in this case cyanobacteria, that are held together with ooey gooey slime, which is really gross. But it's really cool because it means anything that got covered up with that microbial mat was not messed with. So anything that died and got covered up We have beautiful soft tissue preservation. Some of these fish and stuff that they find in this area have their eyes preserved, their muscles, different pieces of skin in their digestive tracts. So very, very good, it's a very good place to find soft tissue. So with all that info, we can imagine that Las Ollas looked kind of like the Everglades, kind of like this picture behind me, just, the Everglades would be minus the pterosaur. And so a lot of the animals of Las Ollas are similar to something like the Everglades. You get, marine invertebrates like insects and crustaceans and bivalves. And then you see things like fish and amphibians and crocodiles or crocodilomorphs on the vertebrate side. And the crustaceans are very important because when we look at these microscopic little shrimp-looking guys called ostracods, they notice that they are preserved with their carapaces closed. And that is something that I don't know much about, but the scientists who did notice this know much more about it and deduced that that means that the current was very, very gentle there. Just like those thin lamination layers also demonstrated. So we got multiple lines of evidence confirming this. Then we also have a lot of evidence just of a lot of crocodilomorph activity. So the crocs were doing a lot of the preying on all of these lower species on the trophic levels. We've got a trackway from a large crocodilomorph pushing itself along the bottom of the water. There are a lot of coprolites containing a lot of fish that are found here. So there's a lot of evidence for all these trophic levels interacting. But finally, we get to the dinosaurs. There are only 3 types of non-avian dinosaur found in Las Ollas, which makes it pretty easy to talk about. They're all very cool. So first, they found an articulated leg of a relative of Iguanodon called Ankylosaurus. So that's this guy in the background here. They found an articulated leg with all the pieces just in place like it would be during life. So once that leg, I guess, got ripped off the body, it got covered with that microbial mat, and you've got this really, really nice fossil of that leg. And then we get Pelecanimynus, which is really, really cool. And it's a relative of Gallimimus of Jurassic Park fame, which you'll learn about next week. So it's these theropod guys in the foreground here that are very skinny and weird. These guys, the skull is preserved with soft tissue, showing it had a fleshy crest on its head that had no bone in it whatsoever, so we wouldn't have known about it if we hadn't seen this tissue. And then it also had a pelican-like throat pouch on that fossil as well. So it was probably, gathering up fish and cool stuff in the water, maybe dealing with those crocodiles at the edge of the water when it didn't really want to be eaten. So this is two very, very cool things we learned about this animal from that soft tissue that we wouldn't have without it, which is awesome. And then lastly, the last dinosaur that we find there is Concavinator, this big theropod here in the middle. Concavinator is a large predatory theropod dinosaur, and it's very cool because it has these 2 vertebrae on its back that stick up way higher than the others, forming this big triangle-shaped crest, just for fun, I guess. They don't really know why, it's just cool. And it also preserves some soft tissue on its feet. It's got cute little, toe pads on its feet. And interestingly, there is a single trackway of a dinosaur, track at Las Ollas. And it is a 3-toed theropod, about the same size and shape as those toe pads on that Concavinator. So they think they have the cause of those trackways right there. And if we used Concavinator as the track maker, using the height of Concavinator with the spread of those tracks, they think it was walking around at a nice 8 miles per hour. And there are several species of enantiornithine birds that are found at Las Ollas as well. And that's its real claim to fame. People are really excited about those birds because it tells them a lot about bird evolution. These are as birdy as you can get, but just with a couple little teeth and little bits of claws on their wings still. So very, very important stepping stones that kind of round out this habitat, which is really cool. So after seeing all the different types of dinosaur, how they spread across the earth, and how we know all that stuff about them, you'll have to come back next week to see how your favorite dinosaur movies got all that stuff wrong. And certain parts that they got right. They did, I gotta give them some credit. So come back next week, same time, same place, to see Taylor McCoy talk about dinosaur species of Jurassic Park. And we'll open this up for questions before I run off to Canada to go make some maple syrup popsicles in the snow. All right, what questions do we have? Yes?
I remember that over the years there have been some real mistakes with reconstructing dinosaur fossils.
Mm-hmm.
And they actually, for maybe decades, had the wrong head on the wrong thing.
Mm-hmm. So, yeah, we do often get mistakes made in the field of paleontology, and it's that darn taphonomy that usually is the culprit, where two different animals got mixed together, and sometimes they accidentally use like a piece of turtle as the wishbone on a velociraptor relative, and they have to go back and publish more and say, hey, we got it wrong. And that's kind of the point of science, is to be able to go back and correct yourself and put it in literature so people can see that that information is out there. But it is, as just a fan of dinosaurs in general, it does get pretty annoying when you're like, I like this dinosaur this way, and then they say, oops, actually, oops, actually, oops, actually. So like the dinosaur Spinosaurus has changed a lot in the past 10, 20 years, and it's getting really annoying. Because, you know, every time people are like, this is what it looks like, and someone paints a picture of Spinosaurus or puts it in a video game, it'll change. And then the people who make that video game get thousands of messages from annoying dinosaur fans who are just like, when are you updating it? It's wrong. And as someone who works with some sort of dinosaur video games, it gets really annoying. But, you know, science marches onward. It doesn't slow down just because we want it to. And it's always exciting when we learn new things. I remember watching a video from this paleontologist who was talking about Dinochirus, that really weird relative of Gallimimus that has the humpback and like really long arms. That was just a plant eater that hung out in the water. But all they found of it at first were these giant arms, and no one knew what to make of them for the longest time. And then there was a conference where there was a presentation about Dinochirus and what it actually looked like. And the room was just packed with tons and tons of different scientists who really wanted to know what this dinosaur looked like. And the amount of excitement, and just like you could hear a pin drop that he described when they were putting these images on the screen of the skeleton, and then finally the final portrait that they got made of this animal, was just the most incredible thing, because we learned so much of it just with that new specimen that came out that changed the way people thought about it. So it is annoying seeing things change so much, seeing errors being made and getting fixed and things like that. But it is really fun and exciting if we can put aside how attached we get to things. Anyone else? Yes?
The woolly mammoth.
Yes.
Is it part of the dinosaurs, or is it more recent?
Woolly mammoth is a mammal that is much more recent than dinosaurs. So as a mammal, it's not a dinosaur. It evolved much later. But it lived in like the Ice Age, we like to call it. So, you know, I think the last mammoths went extinct like while the Egyptian pyramids were getting built. Like very recent animals, compared to dinosaurs, which went extinct 65 million years ago. Another question back there?
Were all dinosaurs egg layers?
Yes. We don't have any reason to believe that they gave live birth. We found many eggs. We found some eggs inside the bodies. I think sharks are called ovoviviparous, where they have eggs They kind of lay eggs inside their body, and then those eggs hatch inside the body, and then they give live birth, even though they had eggs to begin with. We don't have any reason to believe that dinosaurs did that, but there were some marine reptiles, like the ichthyosaurs, that are often lumped in with dinosaurs that did do that. We have specimens of ichthyosaurs with baby ichthyosaurs halfway out of the uterus. That this thing died in childbirth, and both mom and baby got buried, and we have both of them. Which is why we know that they gave live birth, which is really cool. But dinosaurs, yeah, all we know about dinosaurs is that they laid eggs. Any other questions in the room? Were there any from online?
Any online about?
No? Hope I did a good job then.
You did. Thank you.
Yeah, no problem. Oh,
Where's this place located? Shows at the end,
Las Hoyas. It's in central Spain, I believe. So hence the Spanish name. But there's Lagerstadt from all over the world. Like one of the most famous is from Germany, and that's where Archaeopteryx is from, which I guess is why they have a German name for this kind of fossil site. But yeah, there's a ton of different Lagerstadt out there, and I was looking at a bunch of them, like which one would be the easiest to talk about. I settled on Las Hoyas, and it's a Spanish one in Spain. It's pretty cool.
Any more? Okay.
Okay, pop quiz time?
Yeah, we're in quiz. Let's thank Lindsay again. So, this is how it will work. Don't shout out the answer. I have several questions here. I'm going to ask 3. And raise your hand. And Lindsay's going to call on the person because I will not be accused of.
Oh no.
So here's the question. Are you ready? What kind of rocks are fossils found in? Raise your hand.
We'll go with the first hand that came up.
Sedimentary.
Yes.
David, you've won a pizza.
Sedimentary regulation.
Yeah.
Pizza for 2.
Raise your hand. What is a gastrolith?
First hand.
Rocks that they find in the stomach contents.
Yeah. I saw you taking notes too.
Pizza for Harold. There you go, buddy. All right. Now for the last question. This fabulous Ohio County Public Library water bottle. Is it a water bottle?
Yeah, that's what it is.
The question is, what is a coprolite?
Coprolite. What is a coprolite?
Poop.
Yep. Poop.
I have to make somebody say it. Let's do that. John, you want to first?
Yeah, cool.
Thank you.
Of course. Thank you.